I don't have it. I mean, I'm going to be honest with you. If you find it, let me know. I'll have to figure out something to do. Anyway, he's not here today. Okay. So no questions, right? Therefore, I can continue. So here's what we're going to do. Now, in Whitmore's book, he covers this, but I want to go through this methodically and show you how to go about this. And this is going to be a reduced complexity version. This is going to be for anything where you have a termination that's either a capacitor or inductor. We're not going to go beyond that. Let's do it this way. We're going to have a voltage right here. You can just call this Vs. Doesn't matter what it is. I'm going to assume you have a resistance Rs right here. Then we're going to have a switch. At t equals 0, it's going to close. Come over here. And now, here's our transmission line. And we're going to have a load. This time I'm going to put a capacitor, just a capacitor. We can put an inductor too, but I want you to just follow me on the train of thought, the way I'm doing this. This line is going to have a characteristic impedance Z0, and I'm going to make Z0 equal to Rs. Now the reason I'm doing it is to reduce the complexity of the problem. When I throw that switch, we know a wavefront's coming down this way. And it's going to hit, and some is going to reflect. You all follow me? But when it hits here, the reflection, or the transmission, the reflection coefficient is 0, so nothing will be reflected. You all follow me in that class? How many understand it? If this Rs is equal to Z0, then there's no reflection here, because the reflection coefficient going this way would be Rs minus Z0, which would be 0 over the sum. You all follow me? So we're only taking a look at one propagating pulse and what would happen here. Now, this is going to have a length L. And let's assume the velocity on the line is c. It doesn't have to be, but that's really, it's of no real consequence. It's just the time delay. So now we find the time delay it takes to go from one end to the other, and that would be the length of the line over c. I think everybody's got that down. You follow me, class? After that, the next thing we're going to do is we're going to write the equation for the voltage here at the load as a function of time. We're not going to work on the time delay, but I'm going to show this. Now, if you think about this, first we have to find V prime that would occur once that switch is closed. Do you all agree with that, class? It doesn't matter what you call it, I'm calling V prime. So V prime itself would be equal to Vs. Now just look at this. Since Z0 is equal to Rs, it's exactly half that. Do you all see that, class? Normally it would be Z0 over Z0 plus Rs times Vs, but since Z0 and Rs are the same, it's 1/2 Vs. So this is simply Vs over 2, right? So over here, that's the voltage that will be developed. That's simply Vs. By the way, if you're coming in late, the quizzes are being handed around when they finally go. Where are the quizzes right now? When they're done, would you do me a favor? When you get them in the back, bring it up here to the front, and then you guys can get yours. So this is going to be Vs over 2. That's the magnitude of the voltage that will, of the waveform, incoming waveform that hit there. It would be delayed by t minus td. So if we start a u at t function that would have to do with the value of the voltage when it actually strikes the load, or it hits the load, would have to be time delayed by that. Then you're going to have this multiplied by 1 plus the reflection coefficient of the load. Do you all follow? You're going to have an incoming and an outgoing pulse that would occur at the same time. With me, everyone? Now, here's where it gets interesting. We don't have a resistor on the load. So what we do is, we're going to say this has an impedance of 1 over Cs, or 1 over Sc. Do you all remember doing that? Laplace domain, right? It could be 1 over J omega C, or 1 over Sc. How many remember that? Right? You had this. You don't remember it? You remember using S in the Laplace domain. Impedance would be 1 over Sc for a capacitor, would be SL for an inductor. How many remember seeing that? You should have, everybody should have seen this. I don't know. Did you get in circuits?
did it like one day in circuits.
All right, well, here's the deal. Wherever you used to have a j omega, you replace it with s, because technically, if you think about it, s is sigma plus j omega, so just let sigma be 0 for the problem at hand. Or, yes, sir?
Sorry to interrupt. I was just going to say that I had signals over the summer. It goes into great depth, like 2/3 of the way through. There's a lesson. Anyone who's in signals now will, in like
All right,
2 weeks, will have it.
When I teach signals and systems, typically, all the circuit problems we do, we use like 1 over SC for the reactance of the capacitor and SL for the reactance of the inductor. It's the normal way to do business. It really is. Okay. So now when I take a look at this, the reflection coefficient right here is going to be, and we're going to go to the estimate in a second. Let me go ahead and do this first. Now, we'll go to the estimate, but let me put this in terms of the actual estimate right here. So this is going to be, we're coming into the capacitor piece, which is 1 over CS minus Z naught over 1 over CS plus Z naught. Now I'm saying the impedance of this is 1 over CS or 1 over SC. Y'all with me, class? I'll do something and take this whole thing to the frequency or to the estimate in 1 second. That means gamma L here can be rendered as 1 minus, and you can put it S times TC over 1 plus S times TC. And here TC is nothing more than Z naught times C. Now, the reason I did this is just to reduce the number of times I have to write Z naught times C. Everybody's following me on this, class? Now, come over here. We're going to go to the frequency domain right here. We're going to estimate. We're going to take a Laplace transform there. All with me? So now we have VL of S. The Vs over 2 stays the same. And now, you don't remember with Laplace transform, sometimes I have to go through this. If you have U of t, that goes to 1 over S, and I suppose I could define the Laplace transform f of s by definition as the integral from 0 to infinity of f of t times e to the minus st dt. You don't remember that? It's just a fundamental definition that you use over and over again. So it's going to be this, but if you have u of t minus td, that's a time delay, and so you get 1 over s e to the minus, and it's going to be std. You remember this because it's a phase shift? How many remember that part? You had signals and systems, right? Remember Laplace transform? 1 over s is u of t. If you have a time delay, it's just e to the minus. It's whatever the 1 over s is times e to the minus s times t, because that's the time delay. Y'all remember that?
We're in signals right now. We don't get to that subject for another 2 weeks.
You don't have to take signals and systems before this class?
That's correct.
Well, I'll do my best to make it clear. Trust me on this one. I guarantee you, you have this, right?
Yes, sir.
You remember that?
Yes, sir.
You're going to remember. Promise you guys.
I mean, I had it like a couple weeks ago.
Now, this U becomes 1 over s, and then it's times e to the minus st. I'm glad you told me that. I thought everybody had signals and systems before they took them. It used to be that way, and you had to take signals and systems before you took a random signals and systems. But I don't know if that's the case anymore. How many are in random? Okay. You have Bashir?
Yes, sir. Yeah.
Okay, well, he's a very smart guy, so he will keep you on your toes. Next, we're going to take a Laplace transform of this. The Laplace transform of 1 is 1, plus the Laplace transform of this gamma L. I could write the diffie q, but there it is. So it's 1 plus 1 minus stc over 1 plus stc. Now, the only thing I've done is where TL is, remember, I'm doing a Laplace transform of everything. Y'all follow me on this class? Just take a minute, convince yourself. Nothing fancy. This thing right here, I guess. I thought you had Laplace transforms and differential equations.
At the very end of that class. Some people might not have gotten to it.
Okay, anyway, trust me, this is going to be something you're going to live with. Your bread and butter is going to be solving differential and integral equations with Laplace transforms, Fourier series, and out. That's engineering in a nutshell at the higher level. And your whole senior level course is communications, random, and random you're going to do a ton of this stuff, but later on. Okay, you get to this, Now we're just going to reduce the complexity, all right, of the thing, and then we have to do something that you haven't had signals and systems. It's going to be a little foreign to you. It's called partial fraction expansion to get the final. So I'm going to erase this right here so I can do it. All right. Now, S, remember, yes, I put this here. S is really just equal to sigma plus j omega. I don't have time to go into all the theories. Sigma has to do with the real value, and its value actually has to do with the region of convergence that's way beyond the scope of this class, if you haven't had it yet. But j omega you're familiar with, right? You're familiar with that in terms of the value. All right, now if I reduce this right here, what do I get? Take a look. I get V of S right here. Well, you can see right here, what happens here? I multiply 1 plus S tau C times the 1 and divide it by that. Do you all follow me on this? All right, if I do that, I'll put it right here. Hopefully I can get it in here. So now I have 1 plus STC over 1, plus STC over 1 plus STC, right? Now, this is a common denominator. Then you can see 1 plus 1 is 2. STC minus STC is going to be 0, so I have 2 over 1 plus STC. I'm trying to save board space here. So this is going to be 2 over S plus, 2 over 1 plus STC. Are you all with me on this one? Again, my motive here is to get it down to something where I can do partial fraction expansion on. How many have heard of partial fraction expansion? I would think everybody has, but maybe some of you don't recall it. It's okay. Well, I'll get you through this. All right, when I look at this, one of the things that just jumps off the page is those 2's cancel, right? Here's just a tip. Anytime you have things that cancel, so you don't have to carry them out. All right, just get rid of it. I'm going to get rid of that 2 and put a 1. Everybody with me? Now, after that, what I'm going to do is kind of clean this thing up so I can do something called a partial fraction expansion. Down here, I need S by itself. I need S plus a constant. So I divide top and bottom by 1 over TC. And here I get 1 over TC, 1 over TC plus S. Y'all follow me on that? And again, I'm just getting it ready to do a partial fraction expansion. Everybody? No?
I'll just look up the form of on the internet. I do know what that is, but the form looks different.
What the problem?
Just like the standard form of the partial.
Don't worry about it. I don't know what you're looking at, but this is right.
Oh yeah, I was just trying to correlate both to each other.
When you do an expansion, you want to get S by itself, because that's going to, when you go to the go back to the time domain, then you can get the actual time domain form very easily. So here, I'm going to have V of S is equal to, and I'll put it out front, e to the minus STD. That's nothing more than a time delay right here. Then I'm going to have the quantity Vs right here, and it's times 1 over S and 1 over TC over 1 over TC plus S. And now, what I need to do is a partial fraction expansion of this first. Y'all follow me? Now, if you haven't done partial fraction expansions, let me give you, how many have done that? Usually you've done this stuff in some way, shape, or form. I don't know what they called it, but solving for roots. So if I look at this, I'm going to just do it this way. I have 1 over S times 1 over TC over 1 over TC plus S here, right? Now there's something called a pole that occurs. How many know the term pole? What is it in your own words, anyone? It's a value of S that makes the function go to infinity, right? Think of a pole being stuck under a tent, all right? And the tent itself being the complex plane, the sigma plus j omega. At a pole, the value of the function goes to infinity. That's really easy. So here, there's one pole at S equals 0. Do you all see when S is 0, this goes to infinity? And there's another pole when S is equal to minus 1 over TC. Do you all see that, class? So what you can do, because these are two simple poles, you can say this can be equal to some constant A over S plus another constant B over S plus 1 over TC. And we're going to solve for these constants. How are you going to remember that now? At least something akin to that. You had to do this in your math classes. This is like even common. All right, now, how do you get S? Does anybody remember? Well, you know it goes to, this one goes to infinity at S equals 0. Do you agree with that? So here's what we do. That's a pole at S equals 0. Multiply everything by S. And then let S go to 0. And then let S go to 0. Now, you see this goes away. You all see that right there? S is 0. 0 times anything is 0. Do you see that? And what happens? A becomes what? Just 1. Isn't it, class? You all see that? Because 1 over TC divided by 1 over TC is 1. So that means A is 1. So I have 1 over S. I'm going to replace the S I erased. And now, how do we get B? Take a guess. It's, what do they call it? The cover-up method? How many remember hearing the cover-up method? Anybody? What they say is you cover up the pole on this side. The pole is going to be S plus 1 over TC is 0. That's S equal minus T 1 over TC, right? Cover it up, and then evaluate what's left at minus 1 over TC at the pole. Do you all see that? With me? Can you see the far back guy? All right, so that's going to be what? That's 1 over TC over minus 1 over TC is minus 1. All right, so this is going to be minus 1 over S plus 1 over TC. So that is the expansion of this stuff in terms of two single poles. I'm going to have to do this right here. I'm going to take it back to the time of the day. If you haven't had the Laplace stuff yet, I mean, if you haven't had this in signals and systems, don't worry about it. You're going to see this. It's a trivial problem, right? Really. So now I take that V of S, and I say it's equal to just V of S here, and it's going to be times e to the minus STD. This is in this S domain. And then I expanded all that over, and I have 1 over S minus, minus 1 over S plus 1 over TC. Y'all follow me? Now, you don't know. Yes, sir.
Just a little bit, can you go back to the let S approach 0? So if you have 1 over S, how does that work? I might have missed
Watch, I multiplied everything, I shouldn't put it here for this one, right? First, I multiply everything by S, right? With me? Now let S equal 0, what do you see?
Okay,
That goes away, and A becomes what? Just 1 over TC.
gotcha.
That's it. If you haven't had it yet, you will see this. This is a very trivial problem in signals and systems. And at the higher levels, you're going to be doing this kind of stuff all the time. So now, just mention this. Over here, I showed you a relationship between U of t. This is time domain. That's what it would be in the S domain. U of t minus TD would be this, right? Now, in general, anytime you have a function that's time delayed, it's just this phase thing that occurs right here. But the key is 1 over S. So if I have simply U of t, it goes to 1 over S. I'm going to tell you that. How many know that, by the way, from prior experience, from differential equation stuff? You should. You'll get to be very familiar with this. And if I have e to the minus AT U of t, anybody remember what that goes to? We can do it. We can do it. Anybody?
U of t plus a.
1 over S plus A. Okay, that's all it is. You can do that integration quickly right there, and it will. That means if I have this and I wanted to go back to the time domain, it would be u of t. If I have this and I want to go back to the time domain, it's this. There's one slight difference. You see that e to the minus std? That means all the functions, when they go back to the time domain, will be delayed by td. So when I go back to the time domain, I find VL of t is equal to V of s, that's there, and then this one is going to be u of t minus td, and this one is going to be minus e to the minus, and it's going to be t minus td right here over tc. Erase this. And then it's going to be times u of t minus td. Now I can take the u minus td outside of that, and if you look at this, it becomes simply Vs here, and it's going to be 1 minus e to the minus quantity t minus the time delay over the time constant times u, or then the whole thing is times u of t minus td. Are you with me on this, class? That's the solution. What does that look like? Now just think about what's really happening. When I throw that switch, right? No real DC current can ever get through there, right? So as that waveform comes down here, it's going to start charging that capacitor up. And it's going to charge it up until it can't charge it no more, or when that value is equal to Vs, and then it stops. That waveform right there looks like this in time. If this is time, and this is V loaded t, nothing happens until you hit TD. At TD, it's 0, because I have 1 minus e to the 0 right here, TD, which is 1. And then it starts asymptotically approaching a steady state value here of Vs. That should make sense to you intuitively. Do y'all follow me? That's like a capacitor charging, an RC capacitor charging problem, right? You have a resistor in series with a capacitor, and you throw the switch. The capacitor's voltage asymptotically approaches the source voltage, but it's limited by the resistance and capacitance time constant. That's all it is here. Just out of curiosity, that's what it is. That's what it'll look like for a capacitor. Without going through this right now, I'm going to wait until you get your diffie Q, and do tell me when you get this. What happens if I have an inductor? Whitmer's book has this. An inductor has an impedance of SL, doesn't it? How many know that? All right? I mean, instead of J omega, just put an S, right? Now, what happens with an inductor that you know? Well, an inductor, the minute you try to stick current through that, it won't let it, right? It will not let an instantaneous change of current occur. It means the voltage on this thing at t equals 0, just at the instant when that voltage waveform hits it, it'll look like an open circuit. So right down here, you're going to get a maximum voltage, which will be Vs, at t equals TD, when the time goes, when the waveform hits. And then what does an inductor look like as time goes to infinity? Think of the impedance. Class? Short circuit looks like a wire, doesn't it? That means the voltage will go to 0. And if you looked at the inductor one, it would do this. It would come here, and then it would go straight up and then asymptotically approach 0. It would be the inverted curve, you might say. Y'all follow me? I'll spend more time on that once you guys, when do you think you're going to get through your Laplace transform stuff? When you do, please let me know, and then I'll finish up this. Because here's the deal. If I put an R in parallel with this, and a C in parallel, or say a capacitor and a resistor in parallel or series, then if you don't understand Laplace transform theory and partial fraction expansion, I can't do that problem effectively. I get you too confused. Okay? All right, now, y'all follow me on this? I'll give you 1 or 2 simple problems to try to chew on this stuff. Now we're going to go into chapter 3. Chapter 3 is real basic physics and its applications to electrostatic. Now, everybody in here has had electrostatics, right? And the one thing nice about electrostatics, everything's simple in terms of what happens if force laws, all these things are fairly straightforward. It's almost like statics. The actual, or actually, it's very similar to the forces of gravity because the force laws are proportional to 1 over r squared. So we'll start with the most basic idea. This is in chapter 3. I'm going to say this again. Is Cole Carroll here by any chance?
He's not here because somebody broke the window out of his car.
Oh.
Yeah.
All right, well, if you all see him, let me know, will you please?
Yeah.
I'm just having, let me get a hold of you for next class. All right, so chapter 3, and you have your books, I hope. I want to tell you, this is a lot like what you've already had. All right, so we're in chapter 3. This is electrostatics. First, he talks about a little bit about the coordinate systems. I think everybody knows Cartesian, cylindrical, and spherical in terms of what they are. And you know how to add, you all know how to add vectors, right? Add, subtract vectors have, it's like velocity, it's got a direction, right? As well as a magnitude. We'll talk about Coulomb's law next. Now, Coulomb's law, I want to say this, with electromagnetics, everything that I'm going to give you as laws are based on measurements. They're not based on, you know, Moses didn't come down from Mount Sinai to curl a bead. It's majesty bead. None of that stuff. What happened is they're based on measurements. We found a mathematically accurate, almost exact way of representing it. So remember that. It's based on measurement always. So the first thing is when we have two charges called Q1, and we have some Q2, and this you know very well, and they're separated by a distance, call it R, here. Then there's going to be a force on both of these particles of the same magnitude, and the direction has to do with the charge sense. In general, if they're both plus, I'm just going to put this down here, we're going to get a force here on charge 2 that is going to be equal to Q1, magnitude of Q1, magnitude of Q2, and typically it's 4 pi epsilon naught divided by r squared in the AR direction. Here I have to spend a little time, and I'm going to give you a lot more exactness in a second. The exact same force will be on this one, but in the opposite directions. So F on charge 1 would be equal to Q1, Q2, over 4 pi epsilon naught, magnitude of r squared in the AR direction, but I'm going to make a caveat here. I'm going to call this AR21. That is a vector, a unit vector pointing from the first charge to the second. And here, that AR, I'll call it 1, 2, is going to be a unit vector pointing in this direction. And that'll work. Yes, sir.
Oh, what do you have to the right of diffraction?
What's that?
Yeah, what is that? What is that?
AR12. It's just a unit vector. I'm going to spend some time right now talking about unit vectors. So in general, when we have vectors, I've got to define how you calculate a vector and then how you calculate a unit vector. If you have 2 points, I'm going to call this point 1, and it's got some x1, y1, I've got a point right here, 1. And I've got some x1, y1, and z1 here. And then I have a point 2 right here. And this point has x2, y2, and z2. Now, if you want a vector directed from point 1 to point 2, in other words, this is going to be my vector. The arrow tells you the direction. I'll call this R21 because it ended up at 2. It started at 1. It's not real important, this symbolism here, but you have to understand why I'm doing it. And the arrow tells the story, right? Here's how you get it. You say that R21 vector would be it's always the coordinates you end up at, which is x2, minus the coordinates you came from, x1, and then you put a unit vector, ax, here. Now, ax just has a magnitude of 1, but it's pointing in the x direction. Do you all follow me on that? How many heard of unit vectors? Everybody here should have. All right. Plus, and you can see this is going to be y2 minus y1, ay, plus, and then it's going to be z2 minus z1, az. Now, that is a vector from the first to the second point. That's all it is. If I want a unit vector, from point 1 to point 2, I'll call it AR21. Then I take the actual vector R21 and I divide it by the magnitude of R21. You're familiar with the symbol for magnitude, right? Well, how do you get a magnitude of a vector if we have any kind of standard right-hand coordinate system where all the coordinates are orthogonal to each other? That's right, you square the values, right? So this in itself is going to be this vector. I'm not going to write it all out. It's R21, and it's divided by the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And that would be a unit vector in that direction. Everybody with me? Now, something else I'm going to just mention that you probably know from physics. I intentionally didn't put a coordinate system here, but I want you to see this. If the charges Q1 and Q2 have the same sign, they repel. You all know that, class? So if they're both positive or both negative, they're pushing each other apart. But if they have opposite charges, they're pulling together. Everybody clear on that? One other thing about any of these problems, all these things have to do with linear time invariant systems and the way you analyze them. You're in signals and systems, or you had signals and systems. It means if these are two charges, let's say I add a third charge, call it Q3 here, all right? And I want to know what the force is there. Well, I can say there's going to be R 2, 3 here would be a vector from here to that point. You all follow me? Now I can say this is F2 caused by 1. I can say F2 caused by 3. Now that it's going to be Q2 times Q3. Now it would be AR23 over 4 pi epsilon naught. Magnitude, I should call this magnitude of R, call it 2,1 here. And it'd be magnitude of R23 squared. Do you all follow me? Something I failed to mention is what epsilon naught is. Epsilon naught is a constant, right? I'm going to show you a trick here. I want you to be careful. Make sure you pay attention. Epsilon naught is usually rendered two different ways. One is 8.854 times 10 to the minus 12 farads per meter. That is an approximation. How many have seen that one? Okay. Or it's equal to 1 over 36 pi times 10 to the minus 9 farads per meter. This is not exactly the same as that, but they do this for a reason. Because you're going to see there's a mu naught coming up, and mu naught is 4 pi times 10 to the minus 7 henries per meter, and we're going to be multiplying epsilon and mu together, and it'll cancel the pi's. So that's the reason they do it in terms of pi. They're both approximations. Anyway, that's epsilon naught. What does epsilon naught really mean? Epsilon naught is in free space, and you're going to see later on has to do with the capacity of space to store electrostatic energy that we'll talk about later. Epsilon naught is based on measurements. Okay. And that is for the vacuum. If there's nothing at all in space, that's what epsilon naught is. Now, how many have seen epsilon naught in one form or the other? And you should have in physics. If you've had physics, any modern physics, I mean, any course that covered electrostatics, they should have talked about this. And it is determined by measurement. So this is the force laws in general. I'm going to give you some problems, but you probably have had all these problems. If I want the force on a charge and I give you two other charges, you pretty much can get it. You're going to find the force from the first charge system, first charge caused at the second charge caused, or whatever charge it is caused at the second, add them together vectorially. You hear me? I trust you can do that without much problem. Next, we're going to talk about the electric field and why this is the electrostatic electric field. This is on page 124. And why it's so important. And one thing it does is make life easier. So now erase this. I know this seems boring because you've had it before, but I have to do this primer on this one, or else somebody will probably not remember some subtlety, especially about unit vector. This one you don't need to write down, just listen, I'll tell you what to write down in a second. So we talked about the last time force. Well, if I have a charge Q1 here, and I have a charge Q2 here, and now I'm going to have R21 here, a vector. I know the force on this one, right? The force on charge 2 caused by 1 is equal to 1 over, actually, let me do one other thing too. You can do this, you can say K is equal to 1 over 4 pi epsilon naught. Remember how there's always that 1 over 4 pi epsilon naught occurring? Well, K is equal to 1 over, just watch, 4 pi epsilon naught. Well, epsilon naught is 1 over 36 pi times 10 to the minus 9th. Y'all see that, class? You'll notice the 4 pi 36 pi, you can divide 4 pi into both, you get 1 over 9, right? So this becomes 9 times 10 to the 9th. And instead of writing 1 over 4 pi epsilon naught every time, you can just put 9 times 10 to the 9th. Did they do that in your physics course? Anybody? A lot of times they do it to simplify it, streamlines it. But I'm going to put down the 1 over 4 pi epsilon naught, right? And then it's going to be, actually, let me do it this way, it's going to be Q1 times Q2 over the magnitude of R21 squared AR21. Now that's the force. What we can do though is this. Now you remember, if there's other charges that have the same exact form as this, so it'll be Q1, Q3, AR23, R23, you all follow me on this? But everything right here can be reduced to something. If you divide out the value of charge Q2 here, then you get something called the electric field at point 2. Now the electric field is nothing more than the value of the force at that point divided by the charge where the force is developed. You all follow me on that? And the electric field you've become familiar with. So for a given point charge, or any number of charges, if you have a point charge Q1, and you're a distance, call it R1 here, this is the vector direction, and you wanted the electric field at this point 2, the electric field would just be equal to Q1 over 4 pi epsilon naught magnitude of R1 squared AR1. And if you wanted the electric field there from a multiple of charges, you find the electric field at this point from all the charges, vectorially add them. If you want the force, you just multiply by charge. What you're really doing is eliminating the need to multiply by that charge each time. You all follow me, class? And that's the electric field. How many have heard of the static electric field? important thing to note about that, you can't see an electric field. Well, you can see photons, yes. Photons are very high frequency electromagnetic propagation, very short wavelengths. But a static electric field you can't see. The only way to observe these things or measure them. And usually it is something where you have a certain amount of charge that is going to have a force exerted on it that will develop a voltage across two elements. Now just remember this, yeah, the only way to observe static fields is to develop a force on some measuring device. That's the only way. You can't look at it and see it. And one other thing about electrostatic fields, there's no energy propagated. They're there and they're just there. They're not moving. They have photons. Have you heard the term photons? I don't think you take modern physics, but photons, they call them mini corpuscles that light's made of, or really any electromagnetic event is made of these things. These are called virtual photons. They don't move. They're not real in the sense they have energy moving. Photons from light that propagate have real photons and they have real momentum. That's another story. If you ever get interested in this, I suggest you take the higher level physics courses and quantum electromagnetics and just electromagnetics. It's really fascinating. But this is an applications course where you're going to learn everything you need to work out there in industry. So that's the static electric field from one or many charges, right? Now, in his book, at this point in time, what he does, he'll show field lines. And again, the electric field always points away from the charge. So something that I think everybody has an idea about, but if you have a charge Q1, that single point charge, you come out here, the electric field is always going to be pointing away, right? And the field's value will fall as 1 over r squared. Y'all follow me on that? So the field out here is going to be less than the field here. This is just a general feel for things. That's for a point charge. I'm going to get to a few more. If you have a line charge, a constant value. This is another classic physics problem. If you have a line charge, the electric field, and we'll prove this, will always point radially away from the axis the line charge is on if you assume it's infinite. You all hear me? We'll calculate that in a second. But the E field will be radially away here. It will be perpendicular to. And down here, the electric field will be perpendicular, pointing away, but it'll fall off as only 1 over the distance from the center of that line charge is to the first power. It's not 1 over r squared. We'll get to that. Now, you remember that class? How many do in physics? All right. And then we can talk about a plane. If we have an infinite plane, there's one very interesting thing. That's things that happen right here. This has a given surface charge density rho s, and I know I'm getting ahead, but I'm just trying to whet your appetite for what you're about to learn. A plane has an infinite amount of charge, doesn't it? As a matter of fact, if you have an infinite plane, if I'm up 1 foot from it, it looks infinite. If I'm up 100 miles from it, it looks infinite. It looks the same aspect-wise no matter how far away from it. You all follow me? Anytime you see something like that, then you can reason through it. The electric field will never change in value. It will only change in direction if you're above it or below it. The electric field above an infinite plane will always be pointing away from it, have constant magnitude, and be pointing directly away from the surface, or perpendicular surface. If you're below it, it's pointing in the opposite direction. How many remember that from physics? Good. Now I can move on. Now that I've at least given you something so you get a feel for this. Now he talks about cylindrical coordinates and calculating the electric field from a line charge. And I do have a few minutes. Now, a lot of people don't like different coordinate systems. Don't feel that way. You're going, I'll give you some, I'll give you some of the formulas and stuff like this. But in engineering, electrical and computer engineering, higher level courses, we use these continually to describe scenarios. Cylindrical, Cartesian, and spherical coordinates, just because they very well approximate surfaces that we see in the real world all the time. Now there's actually 10 or 11 separable coordinate systems. If you know what an egg looks like, if we had an egg and expanded and got bigger and bigger, that's called a colloid spheroidal coordinate system. There's a way to describe that. We can get separable coordinates for that. I'm trying to think of this term for this thing. There are parabolic and parabolic elliptical equations. There are all sorts of ways for surfaces to be described that are conformal with some real surface out there that you need to actually describe and then separate a del square kind of equation to solve it, to get actual bits of information you need. So just remember that these coordinate systems are designed to make life easy, not hard, and you're using them continually. They're not a one-time event, so keep that in the back of your mind. Because I've heard people tell me about differential equations. Well, I'm glad I'm done with that. I'll never see it. That's your whole life. I mean, that's it. You're going to be differential integral equations or difference equations and summation. You can't get away from it. So learn to love it or change majors or do something. Let's see a psychiatrist. Anyway, now when we talk about cylindrical coordinate systems, they look like this. You're going to have an axis, the z-axis. This is the axis of symmetry. You're going to have a distance out. It's labeled as rho. That's the radial distance measured from the closest point, if this is a point here, right here, to the perpendicular on that z-axis. Right. Then you're also going to have an aspect that has to do with phi. And if you think about this, if this is the x-axis, let's try to superimpose this. This is the y. If I had a point out here, just try to appreciate this. Well, it would have a distance rho from here to here, but there would be an angle in the xy plane of phi. Can you all follow me in that class? So if you're looking right down the z-axis and you have cylindrical coordinates, you're going to see an x, you'll see a y. Here's your z-axis. But here's your distance rho, and this angle that's measured from the positive z-axis is labeled phi. Here's your point. Now that point will have a z-coordinate. So I have the z-axis here. It doesn't have to be at z equals 0. It's going to be at any point z. You all follow me, class? And the relationship between cylindrical coordinates and Cartesian coordinates is pretty straightforward. Rho in cylindrical coordinates is the square root of x squared plus y squared. We're assuming you have a point described by x and y, and you want to know the cylindrical coordinate values, all right? The value of z is the same in both. Doesn't change. Cartesian to cylindrical. The value of phi is actually, if you look here, you'll see it. Since this is x and this is y, right? Can you all see that there, class? It's always measured from positive x. It's the inverse tan of y over x. Can you all see that? So this is going to be equal to tan minus 1 of y over x. And that's the relationship. I'm out of time. I'm going to send you something that shows all the relationships between differential volumes, differential surfaces, differential lengths, and the coordinate systems from cylindrical to spherical to Cartesian. And that way you'll have it in front of you when you do some problems. I'm going to ask you to do some problems. Now, I know you've had a lot of this class. I know it's not old hat. So I'm going to ask you to do it for a Friday. A good question is, are we going to have a quiz? And that's what you were about to ask, I'm guessing. Somebody should have asked that. You were going to ask that. You get the prize. All right, we're not going to have a quiz on Friday, but we're going to cover it. We can't, really. And the reason is, I don't want to give you the capacitor stuff until you had linear signals and systems covered everything. All right, and I'll give you probably a quiz on Monday.
Do you have your laptop?
Friday's important.
Do you have your laptop on you? Okay.
You got questions, come see me.